Hi there, level 3s. So the first thing I'd like you to do is go and watch a video. It's on YouTube. It's called Simple Harmonic Motion Crash Course, Physics number 16. And it starts off talking about...
In June 2001, officials in London
Right, so what is simple harmonic motion? A few basic concepts before we start is, what is frequency? Can you remember? It's how often a motion repeats itself in 1 second. So for example, if you think of your heartbeat, if your heart were beating at 60 beats per minute, that's 1 beat per second. That's 1 hertz. So the unit for frequency is hertz. What is period? The period is the time it takes for 1 complete oscillation or 1 cycle. So example of the pendulum on the right here, we could have timed it to see how many or how long it takes for the pendulum bob to go to the right and all the way back to the left. So please note, 1 complete cycle is there and back. That's 1 oscillation. How are frequency and period related? And you need to know these equations if you don't already. Period is 1 over frequency and frequency is 1 over period. Here are some examples of simple harmonic motion. So this is obviously in very slow motion, but the prongs on a tuning fork vibrating could be one example. Another example would be the mass on a spring bobbing up and down. On the right here we have piston animation. It's going in the same repetitive motion at regular intervals, and down the bottom here we've got coupled pendulums. That means 2 pendulums on a string, and we'll see that they've got the same period fixed. We'll come back to that later. Another place that simple harmonic motion is very useful is in particles, or the motion of particles. So air particles or air molecules will move in simple harmonic motion. And if you watch one of these particles moving backwards and forwards, you will note that its motion is quite frequent and simultaneous. Here we've got the red. If you follow the red particle on the screen, you'll notice it's making a circle, and that's the pink background circle there. So water waves move in simple harmonic motion as well. Seismic waves are another type of wave which you may consider moves simple harmonic motion. So there are lots of useful applications for simple harmonic motion. Simple harmonic motion can be used to predict what will happen in certain situations, such as seismic activity. So what are the features of simple harmonic motion? Well, as I said, it's regular oscillating motion where the object moves back and forth over the same path. In the middle of that path is called the equilibrium position. So if you follow here, you'll see the mass, center of the mass goes to the green lines at both the top and the bottom. Right? And halfway between those extreme positions is the equilibrium position. So the greatest distance from that equilibrium position to where it is at a maximum point, that is called the amplitude, and we signify that by the symbol Y. Sometimes capital A, sometimes Y. For now we'll use Y. Next we need to look at the restoring force and the amplitude. So the restoring force is always acting towards the center, and you can see when it's at the extreme position, there and there, top and bottom, then the force is acting towards the center of the motion. When the object is in the middle, past the equilibrium position, or in the equilibrium position, then the resultant force is 0, which brings us to something really important, the acceleration. Where do you think the acceleration is at a maximum? Do you think it's in the middle, or do you think it's at the end points? In other words, the amplitude, the greatest distance from the equilibrium. Actually, the acceleration is greatest when it's furthest away from equilibrium, and the acceleration is 0 in the middle. Let's watch a video.
So let's look at some simple harmonic motion. This one we've got it horizontal with 2 springs.
So here you've got
equilibrium is going to be right in the middle. And so as I pull it towards this side, there's going to be tension in this spring right here, and it's going to pull it towards the right. And so that restoring force is going to move it towards equilibrium. Now it's going to move in that direction. Now this other spring is going to move it back towards equilibrium like that. And so what we're going to get is this simple harmonic motion. What's cool about this one is there's an accelerometer with little LEDs so you can see the acceleration of the object. You can see right in the middle there's no acceleration right in the middle. And so what do you have to do in videos like this or in problems like this? You have to be able to identify the position of the object and the velocity and acceleration.
I hope you heard that fairly clearly, but that guy's getting ahead of us. So let's just continue on looking at the features. So hopefully you picked up that the acceleration acts towards the center in both, whether it's top or bottom of the equilibrium, so left or right or top or bottom, so depending on which way your spring goes. And hopefully you understood that the force is always acting towards the center, right? Two conditions necessary for simple harmonic motion, and you need to know these, is that the acceleration is directly proportional to y. So, and the further the object is away from the equilibrium position, that means the acceleration is going to be more, and acceleration is always directed towards the equilibrium position, and you can see this by the direction of the arrows here. So if we write that, it can look like this. A is equal to negative ky. So what is the k here? It's a constant. Why do you think it's negative? Any ideas? Well, if the y is in a positive position, so let's say this was 0, equilibrium was 0, and anything above it is positive, well, then the acceleration is going to be in the negative direction. However, if y is negative, the acceleration will be in a positive direction. So, at equilibrium, the mass has got, so when the mass passes through the equilibrium position, it has 0 acceleration and a maximum velocity. And at the end positions, where the lines are green, so that's here and here, the mass has got a maximum acceleration, and the velocity at those points is momentarily 0.